you count the galaxies now in terms of mass, there's not enough mass to basically explain why galaxies move at that velocity.
The rotation is way faster than
faster.
it should be
Exactly.
with only visible matters.
Exactly.
I see.
Yes. So even with all the matter you count from galaxies, even with the ones we don't observe because we miss them, there's not enough mass to explain those velocities. Right? You need a physical model, right?
Okay.
Basically, you need to say, okay, this star has its temperature, for example, 10 parsecs. The brightness of this star, the one with 10,000 kelvins, you have this magnitude. That's the absolute magnitude.
I see.
100 years ago, Erwin Hubble, he measured that galaxies very far away are receding from our star, getting farther away, right? Yeah. Basically an indication that the universe is expanding. And what he measured is that basically the spectra now of the galaxy is redshifted, is shifted to the red side of the spectra, right? To longer wavelengths. So you have, emission or absorption lines, and they were all like shifted. They took a picture to the center of a galaxy. This is the Event Horizon Telescope. They basically recreate what would it be in the center of a galaxy. That's something that you can also measure with the motions of the stars there. Yeah. And that basically is the picture of the black hole that came 5 years
phenomenal
ago. Exactly. It's
image.
A very nice image.
今回のゲストはホアキン・アラミホさんです。イギリスダラム大学で物理学の博士号を取得。今はカブリ数物連携宇宙研究機構の研究員で、宇宙の巨視的構造の宇宙論シミュレーションと観測の専門家です。僕が小さい時からずっと興味を持っている宇宙の疑問について、世界最先端で研究をされているホアキンさんにいっぱい質問できました。はじめは宇宙の距離はしごと呼ばれる宇宙に存在する天体の地球からの距離の測定方法について話をし、その後ダークマターやダークエネルギーといった宇宙の構造について話をしました。後半はブラックホールの話をしています。好きなところから聞いてみてください。知の隠れ家ではこういった学術的な内容でも知ったらワクワクするような隠れた知を発信しています。今回初めて英語での収録で僕の英語の怪しいところがありますが、英語と日本語どちらも字幕をつけていますので、歯車マークの横の CC ボタンからオンにしてみてください。それでは早速どうぞ。Let's start with the cosmic distance ladder that you have given a talk the other day. So in general, what's the cosmic distance ladder? Let's start with that.
Yeah, in general, it's a concept we use in astronomy and cosmology to describe how we can estimate a distance to an object in the sky, like very distant objects, of course, like the moon, the sun, the stars, the galaxies, and far away. So what we call it a ladder is basically because we build a method that is always based on a previous measurement of another method. So you have method after method that we use to go further and further.
Yeah. Okay. So you need some base, and then in order to get the further distance, you need that theory or that measurement to climb up even further.
Yes, that's kind of like the funny part. Like you start for something very basic, which is just mathematics and geometry, physics, right? And then you go to the beginning of the universe, basically. So you cover the whole universe, and between these different methods, you can estimate distances, like very accurate in the sense of you don't go there with a ruler to measure what's going on, right? You cannot do that. But you have a method that is based on a scientific way to do it, and it's quite effective in that way.
Okay, I see. So one of the most basic thing is the distance from Earth to the sun.
Yes, right. So you have to do something mathematical for that. Like it's usually based on observations, right? But you need mathematics for that. So whatever you can do with mathematics is the most basic thing you can do. To the moon, to the sun, to cross stars, and so on.
I see. I believe we use the mathematics and also the distance from the Earth to the Earth to the Sun,
Mhm.
which is one astronomical unit.
Yes, that's right.
And if I'm correct, I remember correctly, we use that as one of the base measurements, and
Mhm.
then we use math. Maybe
Right.
you can give a talk about the parallax.
Parallax, for example. Yes.
Yeah.
Yes. So you're right. Like one of the bases to measuring distances, like big distances, is to call the distance between Earth and Sun that we know is basically a constant because the Earth revolves around the Sun. We call that the astronomical unit.
Mhm.
It was proposed in the 17th century, I believe, but it basically tells you like, okay, this is gonna be my scale to measure distances to objects that are further, like different planets in the solar system and different stars. Okay, and because of the same reason, like the Earth is revolving the sun, uh, basically you can use what you said parallax, which is this relation between angles and distances, to estimate what is beyond the sun. In that sense, like what's the distance to the closest star to the sun, for example, and that's used with a parallax, basically, which is the distance at what object in the sky covers one arc second in the sky. That's a parsec.
That's a parsec.
Yes.
Okay. So yeah, how far are they in the units of parsec? We can measure with the parallax.
Yes, yes. Yeah, it's a very good question. So yeah, one parsec, to give you the number, is 3.3 light years. So
Okay.
that's the distance the light covers in 3.3 years. It's very far,
That's quite
millions of kilometers, right?
Yeah.
So, and yeah, that is just a fraction of our seconds, right? So you can do this with a telescope, right? But at the same time, you're gonna need a microscope because an arc second is just 1/3600 degrees, right? It's a
Yes.
small part of a degree. So that basically tells you the closest star is already in this micro distance in terms of the eye resolution, for example.
Yeah.
So for further distances, the parallax becomes smaller, right?
Yeah.
So it's not impossible to measure. Astronomers have done this since centuries, but at some point you have a limit. So it's probably in the order of 10 to 100 parsecs, like since we can measure with parallax. And that's the parallax you measure with observations of the Earth at different epochs of the year, like
Yeah.
6 months usually, because that covers a base of 2 astronomical units, which you can use to create this triangle that basically you use to measure the angle with parallax. Right? So yeah, at some point that measurement is more difficult to do, right? So you have to use other methods.
Yeah. But a little bit of side note is that we use that data, which is it has to be quite accurate, and then it's given or obtained by measurement on the ground, and also maybe space telescopes, which are more used
For
in the same.
parallax,
Yeah.
the best measurement of parallaxes are done with a telescope called Gaia.
Oh, okay.
And basically measures all that is visible in the galaxy, stars in the galaxy.
It's space telescope, right?
That's a space
Gaia
telescope.
Space telescope.
So yeah, that will give you the best estimation because you can do better corrections. There is no atmosphere, right? So the way of observing it's far better in the space than in Earth, right?
Yeah.
In Earth, we think we control the what you call a systematic, like what will create an error in your observation, right? So you can do it fairly well, right? It's just that you have to apply more corrections.
I see.
Sense. But I would say everything you can measure with parallax, you can do from Earth.
I see.
Yes.
Yeah. I myself is a space engineer,
Yes.
and I know how hard it is to stabilize a spacecraft in the range of like 1 arc second.
Okay.
And like I really do think like those scientific spacecraft, they gather all their engineering feat into one spacecraft so that they can be.
I see.
Yeah. So
Well, how do you measure the position? Like you take a picture of the object?
in order to measure get the position, you need a star map basically.
I see.
You get a picture of the star, and then you already had a star map in your memory, and then you match
I see.
which field of view matches with
Interesting.
the star map you already have.
Yeah.
In that way, you can basically tell which orientation in the inertial space you were in.
That's interesting. So probably those same stars you use, they need to be corrected by parallax once you do this matching, because it depends on what time of the year you observe them, for example.
Yeah.
But it's cool that you use those same stars as a reference, which is something that we also do. Like,
that's true.
Yeah.
That's true. Yeah, and also like there's a noise, or we have the disturbances that causes spacecraft to get disturbed.
Yeah. Yes.
So it's not it's also important to like not only decide where which orientation is facing right now, but it's all like stabilize.
Right.
It's also it's quite interesting engineering concept that we have to do.
That's very clever.
Yeah.
Yes.
Anyway, so let's get back to the standard. Let's get back to the distance ladder. So even farther, like the stars that cannot be accurately measured by parallax. How do we go even farther than that?
Yes. Basically, then is when you have to apply physics, like a lot of physics.
A lot.
Basically, these things are bright in the sky, like the sun, right? They emit a lot of light and they shine every night, right?
Yeah.
Basically, you need to learn how the star is, its brightness, its luminosity, or the properties of the stars, basically. Because that tells you a relation of how far a star will be shining in the sky and how dim its light get to us, basically. So it's the physical law of the inverse of the distance to the square.
Inverse of
So the further the star, the dimmer the light.
Yeah, until it gets to our
until
place,
we observe
it will get dimmer and dimmer.
Exactly.
Yeah.
So for that, you need to first understand the light of stars that are closer to us, like with the ones we measure with parallax, for example. Once we understand their properties, like the color, their temperature, their size and mass, everything, you say, okay, this is my my base, this is my reference. Okay. So you do the mental exercise. What will happen if a star that is very similar to my reference is now further and further away, right? The light will go dimmer, and you can measure that with the physical law, right?
I see.
So that basically gives you an estimation with a very good error bar of how far the star is in this case. Okay. So in that sense, you don't care if the star is already, in the fraction of astronomical units or in the fraction of parsecs. You say, okay, this is already hundreds of parsecs away, right? So it's a big number, right?
Yeah.
So it doesn't matter how much error you have if the error is small, right? Like the tiny number. So basically, you use that relation to say, okay, now my star is, in terms of brightness, this far away. And this is basically what you call the apparent magnitude. Like it's a logarithmic number, so you need the logarithmic of the luminosity, the logarithm of the luminosity, right? That basically tells you in terms of that number, in terms of magnitudes, how far the star is, and you can call that a distance.
I see.
Effectively. Yes.
I see.
That's what I say. Yeah, you need a lot of physics to do that, basically.
Okay, so in order to then compare with the apparent luminosity, we need an absolute luminosity.
The reference gives you what you call absolute magnitude.
I see. And how do we know that the absolute luminosity? Is there any magic that we can use?
Right. Yeah. True. You need a physical model, right?
Okay.
Basically, you need to say, okay, this star has a given property, like it's a temperature, for example.
Temperature. Okay.
Say all stars at 10,000 Kelvin have this intrinsic brightness, right? Again, with the inverse of the Square's law, you say, okay, at 10 parsecs, the brightness of this star, the one with 10,000 kelvins, will have this magnitude. That's the absolute magnitude.
I see.
So the relation then with apparent magnitude comes always with the absolute magnitude, right? That basically tells you the distance, the relation between distances, only by measuring luminosity. Okay, and that's what we use to measure the apparent magnitude or the distance of most of the stars in a galaxy.
I see.
Yes, it's not only for those stars. Okay, now if the star has a different temperature, you need to do this whole exercise again, right? You need a reference for that star, right? And astronomers, basically what they did is to make this whole zoo of stars that basically is called a color magnitude diagram. That basically tells you, okay, the star by this color and this magnitude will be in this position.
I haven't seen this picture. There's a that's called the main sequence.
Exactly.
I see.
Yeah, main sequence is like the most typical kind of a star you'll find. Then, depending on how the star evolves, can become a red giant, or it can be a blue star as well, right? And then becomes white dwarfs and so on. Yes.
Yeah, I see. But it's also hard. How can we decide which sequence of this magnitude plot?
Just by looking at the spectra of the star, meaning the light as function of its frequency or wavelength, gives you most of the information of what type of a star is and how it evolve in its different stages. Yes.
I see.
Usually goes with the mass. The more massive the star, the more easier to die, like a neutron star or a black hole, right? If it's like what we call a normal star, like the sun, it will become a red giant and then it will become a white dwarf, right? Mostly the mass is what it tells you how the star will behave. The mass plus the spectra. Yes.
I see. And that's the stars quite far.
Yeah.
But is there any farther way we can measure or like we have I think we have other types of stars or supernovae that tells you like the specific that has specific characteristics of periodic velocity.
So far we are in the galactic scale, right? So we can measure magnitudes for all these stars, so we have distances.
Yes.
So you can recreate a galaxy, and that's what Gaia did. They basically took a picture of a galaxy by knowing the positions of different stars, right? And you have this nice video of how a galaxy looked like from above, which is something we cannot see because we are embedded inside the galaxy, right? But Gaia, by measuring all these positions, can do the recreation of how the Milky Way looks like from any position. When you want to measure distances beyond the galaxy,
I see.
you need what is called a standard candle. It's similar to the sense that it's very physical. You need to know properties of objects, in this case, supernovae or Cepheids, right? By knowing those properties, you can also estimate the apparent magnitude, right? And again, because this is something that we study, maybe with a reference, you relate that apparent magnitude to an absolute magnitude, and then you can measure now distances to those supernovae or those Cepheids that could be in different galaxies. Yes. So now, you're measuring distance that are not just in parsecs, but in the kiloparsec scales, thousands of parsecs. Okay.
Wow.
Yes, it goes bigger and bigger what you can measure, right?
Yeah.
And it's just because supernovae or Cepheids are really bright, brighter than normal star. Supernova is literally an explosion, so that's something that's going to be very bright because the star is burning fuel, and it grows bigger, right? And then all that material ignites in an explosion. That's what we call a supernova.
Yeah, but you have to be a little bit lucky to catch that moment.
Super
right?
lucky, yes.
Yeah.
If you do the numbers, you have millions of galaxies as well, probably billions if I remember correctly.
Yeah.
And the rate of supernovae is probably in the order of, like probably a tenth in a year for a galaxy. So if you do the mathematics of that, it's true. It's not something that happens. You have to you have the chance. You need the chance to observe the event when it's happening because it takes a couple of days, right? You can miss it quite easily.
Right.
But if you do the mathematics, you have a fair sample of probably thousands of supernovae
I
that
see.
people have used to measure distances.
I see.
Yes.
But there's no way to, like, for example, predict it's gonna happen in this place or something like that.
I don't know if to predict when it's gonna happen,
So
but you can say this star it's close to the end of its life, so in the next thousands of years it could happen.
okay, that's
So
scale.
it's tricky.
All right.
Yeah, I think it's you have to be more lucky, as you said. You have to capture the event when it's happening.
Yeah,
Yes.
or you have to have large like aperture of
Right. Yes. Something that LSST in the future, this new telescope that's happening, will definitely have, because LSST, what it does is basically to do a picture or a video of the sky,
Mm-hmm.
like thousands of square degrees in one night, and it will do that for several nights.
Wow.
So you're going to have a sequence in time of how bright these stars are in the sky, right? If you see one of the stars is changing its brightness from one day to the other, you can assume something is happening. It could be a Cepheids, could be a supernovae.
Uh-huh.
But yeah, LSST will definitely multiply the amount of supernovae we observe. Yes, because it's kind of like the purpose of the telescope.
Okay.
Yes.
Okay.
You're right. You need a bigger area to increase your chances of finding, in this case, a supernovae.
I see.
Yes.
So yeah, those supernovae and Cepheid variables are standard candles.
Yes,
Okay.
because we, by observations, this is something that's been done in the last 100 years. We know how bright they are as function of time.
Mm-hmm.
Basically, keeps you a relation that you can, using physics again, use to estimate the apparent and the absolute magnitude and measure a distance.
Okay, so that's how you measure beyond galaxies.
Yes, if you
And-
wanna measure distance to galaxies beyond the Milky Way, you better find a supernovae.
I see. I
Yes.
see. Okay, then is there any larger distance that we can measure?
Yeah, of course.
Yeah.
So far, we have our galaxy and closer galaxies, right? That's
Yeah.
what we call the local group.
Local. Okay.
Yes, so that's basically the neighborhood of the Milky Way. Like
Ah.
everything that's in the same gravitational motion imposed by, in this case, the Milky Way.
I see. So galaxies form our local group, and then there are other local groups.
Exactly.
Yeah, I see.
Yeah, so the Milky Way is a very massive galaxy for its group. It's probably the first or second more massive galaxy, meaning that things tend to get closer to the Milky Way. So our neighbor galaxy, Andromeda.
Andromeda.
Yes.
Yeah. They are colliding to us?
They're going to collide billions of years. Yes. And basically that tells you, okay, this is something that I can also measure. I can measure the velocity Andromeda is coming to us, right? Which is also information of distance, right? So yeah, you say in this time, Andromeda will get closer. But yeah, all the satellites, we call them satellite galaxies because they're smaller than the Milky Way. You have the large Magellanic Cloud, the small Magellanic Cloud, and more galaxies. Those are basically the ones we need the Cepheids or supernovae to measure the distances. Beyond, yes, you can still use supernovae because they're quite bright. You can use them until like half of the age of the universe, which is half of the size of the universe we observe.
Quite bright.
Quite bright. So basically with supernovae, yeah, you can measure those and get this galactic map, extragalactic map now that all the galaxies that are close to us. Yes. So that basically solves a big chunk of the universe.
I see.
But yeah, as you said, you can also go further.
Yeah.
For that, you need a Hubble law, basically. So again, 100 years ago, Erwin Hubble, he measured that galaxies very far away are receding from us. They're getting farther away, right?
Yeah.
Basically an indication that the universe is expanding. And what he measured is that basically the spectra now of the galaxy is redshifted, is shifted to the red side of the spectra, right? To longer wavelengths. So you have, emission or absorption lines, and they were all like shifted, right? That would mean like by Doppler effect, is something that is getting away from us. But yeah, what Hubble found is that all galaxies do this in the farther universe, right? So it means that from our perspective, everything is moving further and further away.
Yeah.
And that's Hubble's law, yes. You can measure a velocity, which depends on that distance now.
Yeah.
It's a line. Yeah. Basically, Hubble used that to measure okay, so if it's a line, the constant, which is the slope of the line, is
it's linear.
yes, it's a linear relation.
It's depending on how far it is from us.
Exactly. The
and
further,
it's proportional to
the
that.
faster it moves. Yes.
Okay,
That's Hubble constant.
I see.
Yes. Hubble used that to say, okay, by measuring this constant that he can obtain with this relation, and by measuring the velocity of these galaxies, he could estimate the distance. That we now are talking about megaparsecs scale, so millions of parsecs.
Millions of parsecs. Wow.
Yes. And that basically would be used, the redshift in this case, to measure with Hubble's law the distance of the galaxy to us. Right? And yeah, that's basically solved like 99% of the universe.
I see.
Yeah.
I see. So because we know that how fast the galaxies are receding from us, we can calculate the redshift of
Yes.
the galaxies.
Yes.
And by looking at that, we can calculate how far it is, how far they are.
Yes. And yeah, that basically was at the same time that Einstein came with general relativity. So physicists came to create models of expanding universe.
Yeah.
That would imply there's a big bang, for example, there's a beginning.
Oh, because it's expanding, it should be.
It's growing, yes.
So it should be the beginning if you go back in time.
Exactly.
I see.
Yeah, if you go back in time, you could assume, the best model would assume that everything starts from this small state, which is primordial, is quantum also. So basically, you would call that a beginning, t equals 0, right? And you can use that to also estimate the age of the universe, which is something that Hubble also did, right?
I see.
With a huge accuracy, like very accurate, which is this for close to 14 billions of years that we know.
Okay.
Yeah.
Yeah. So from knowing from having the technique to measure the distance, we also know have the technique to measure the time.
Yes. That's kind of like it's kind of like counterintuitive in the sense of why would it move if I'm not moving on time? I'm measuring right now, right?
Yeah.
No, it's not what's happening. You get the light of objects as light has a finite speed, right? So you get the light of the object as times happens, right? So that basically implies that you have this time where the universe evolved until what we observe now in the closed universe, right? Meaning that if you look further, you're also looking back in time. So you're looking older galaxies, right? And at some point you will have a limit, which is basically what we call the CMB, which is the screen of a remnant of the Big Bang. Yes, the cosmic microwave background.
Okay.
Which is basically kind of like the further we can observe, because it's beyond that, the light wouldn't still reach us, basically.
Okay, so I remember that's because the early stage of the universe, they are so the temperature was so high and particles are going around and you cannot see through in that area.
Yeah, what you can predict from Big Bang, if you do the theory, is that basically all the matter, the baryonic matter, the matter we can observe, what was in such a dense state that photons couldn't travel freely, meaning that they couldn't escape this state, this plasma, right? So as the universe started expanding, right, it became cooler, right? Because it's kind of like ideal gas equation, like the higher the volume, the smaller the pressure and the temperature, right? So basically that implies that the universe gets cooler, right? So there's a time when, because the universe became cooler, this energy also became like lower in the sense of radiation energy. So that was enough for photons to escape. So basically that moment is captured in this CMB, right? And then photons start traveling, matter was already forming, like forming stars, galaxies, and the universe has expanded. It became what we observe now.
I see.
Yes.
So that's how we can see the farthest we can see with our visible spectrum of light.
Yeah.
I see.
Yeah, exactly.
So where are we? We are at the beyond the local group of galaxies and use cosmic microwave background to measure the distance.
Yes.
And there are other things you can use to measure or
Yeah, absolutely. We're in the stage of megaparsecs of scale,
Mhm.
but yeah, we still need to solve this 13.7 gigayears of universe,
Okay,
right?
yeah. Still long way to go.
Yeah, yes. But yeah, for that you need another method, basically. So by measuring this distance to individual galaxies, you create a picture of the large-scale structure of the universe, which is the largest scale where you can measure things.
I see.
So you create these very particular patterns that we refer as cosmic web. It's full of voids, filaments, and clusters and walls. And yeah, at some point, you need information of that structure to say this is the scale of the universe at this time. So it's what we call the baryon acoustic oscillations. So it's something, again, you need a reference for that, right?
Yeah.
Something that you can measure directly from the CMB with the physics, So it's called baryon acoustic oscillation because it's just the pressure that photons produce over the matter in this plasma state before the CMB that basically inflate like a bubble of matter of baryons, right?
I see.
So because this is a plasma and it has a speed of sound basically, which is the velocity the plasma move, they call it acoustic oscillation, right? Because it's effective speed of sound for this plasma.
I see. Wow, interesting.
Yes, that's physical. You can measure by using physics, like primary physics, how big will it be in its space, like at the CMB time. That's like 150 megaparsecs in size.
Oh, at the same.
At the CMB, yes.
Okay.
So by knowing that, now you can use these observations of galaxies to measure this feature, which is what we call the BAO, the baryon acoustic oscillations. This looks like a little bump in the what we call the 2-point correlation function, which measures the distance between galaxies.
I see.
So if you measure this, will give you a little bump that is the same BAO produced in the CMB, right? That will give you a scale that basically you can use to measure a distance.
Yeah, it's like imprinted ruler
Yes.
that you can use.
Exactly. It's not
measure.
Exactly. Like you have to imagine, like yes, at the CMB, this pattern froze in terms of what would it look like in the sky.
Yes.
You can estimate where at what scale happens with galaxies at a different time, right? That basically will give you the apparent size that you can relate to the absolute size, like the real size in the CMB. And that will basically give you a distance. Right?
I see.
So the easiest relation you can use, like, is the apparent size divided by the real size. It will give you something like the distance. Sorry, apparent size is equal to the real size divided by the distance. Yes, which is like the one we use to also measure the distance to the moon or the distance to the sun.
I see. It's like how, because it's, even though sun and the moon looks similar in the size, but it's because it's a different
distance. So the sun is further, it will look smaller, right?
The same
we use
applies
for the BAO.
Yes, it is.
And that basically completes the whole scale of the universe in terms of distances.
So that's how we get to the end of the universe, or how we measure the universal structure or large structure of the universe.
Yes, that completes the cosmic ladder.
Wow.
Yes. Well, now it becomes cosmic because we're in cosmological objects, right? But yeah, you start from the moon, you start from the sun, and you get all the way to the CMB in this case.
Wow. So let's then get into the structure itself.
Yeah.
Which is your specializing.
Yeah, exactly.
As you a little bit mentioned about it, cosmic filaments and cosmic voids.
Yes.
And so on. So in a larger scale, as you said, it's not uniquely distributed, or it's not randomly distributed. Galaxies are like forming some kind of structure.
Right.
Yeah. Can you speak about the generally what kind of structures are they making in the universe? And
Yes. Yes, it's not random, but it's very close to random,
Mm-hmm.
right? Or we
I
can
see.
say it starts from a random.
Starts from the random. Okay.
Yes.
I see. I see.
So basically, the best theory we have to describe this structure implies that you start from a random Gaussian distribution, a normal
Oh,
distribution.
really?
Yes.
Mm.
That basically is what you measure from the CMB. The CMB is almost random, completely random, from a Gaussian, of course.
Okay.
So what you measure is that, if this generates from random distribution,
Mhm.
you have to include in the equation both the expansion of the universe and gravity. Okay.
Mm.
That basically is an evolution that leads you to what you observe today, a redshift zero, basically, today. Yeah. If we understand gravity as a theory with general relativity, for example,
Mhm.
that will lead to this now non-random distribution, right? So it departs from random at some point, which is kind of like we try to understand. But because the way gravity works, which is an attractive force, right, basically will lead to these large structures, right? So basically, the one you can identify more easily is like a cluster of galaxies,
Mm.
basically where everything is collapsing to a very dense
Yes.
center,
Yes.
right? So you have galaxies now that are orbiting a middle galaxy. So for our Milky Way, we have satellite galaxies orbiting, right? So we would know that our galaxy will be associated to a cluster at some point,
Mm.
right?
Mm.
We measure that, like there are close clusters that have more massive galaxies. So Milky Way is probably heading to that direction.
I see.
And that basically tells you like the main object that you can measure in this large scale, which is cluster of galaxies. And you observe them; they're everywhere. Like you see a group of galaxies, it means it's close to a cluster, right? Like with aggregation of in the order of 50 or hundreds of galaxies, right? But it's not the only one. Again, when you solve the equations of gravity for this matter field or galaxy field, you realize that in the way that things collapse,
Mm-hmm.
you can also create a filament, right?
Filaments.
Yes. So filament is basically like a elongated shape
Mm.
made of galaxies
Yeah,
or matter, right?
a series of galaxies
Exactly, in a line.
in a
Yes.
line.
That means that basically you have collapse in directions and you have one perpendicular direction that has a velocity,
Mm-hmm.
right?
Mm-hmm.
So that will be a filament in terms of
Okay. I
a
see.
gravity equation.
I see.
Right.
Wow.
You can do the same instead of now all these directions collapsing. You can do up and down
Mm-hmm.
and have two dimensions that are moving. So you have a pancake, a
Mm-hmm.
sheet.
Mm-hmm.
That's what we call a wall, basically, cosmic wall. Yes.
So it depends on how which velocities are the galaxies
Yeah, it's
facing.
dynamics.
It will
Mhm.
create different. If it's aligning, it will be filaments.
Filament.
If it be
2D,
2D, it will
it's a
be
wall,
this
a sheet.
wall.
Yes.
Okay.
And if it's 3D, things are moving in all directions. So
Yeah.
it will be a cosmic void. We believe cosmic voids are like growing, right? So
I see.
things are moving away from like an empty
From
center.
something.
Yeah.
Yeah.
So that basically moves matter away. But again, it's moving to either a filament or either a cluster, right? But it's getting away from the void. In theory,
see.
a void would be increasing,
I see.
which is interesting. Not all voids are increasing because if you have a void inside a void, that void will disappear at some point.
Mm-hmm.
So that is a collapsing void, right? But in
Yeah, yeah,
general,
yeah.
the void is always increasing. Yes.
Yeah. Okay. So there are certain places where voids, if they are all voids, it will like cancel out or try to like push
Right.
against each other.
Yeah, imagine a little void between two bigger voids. Right?
Yes.
The void is gonna get squashed.
Yeah.
Right. So that's a collapsing void. But
I see.
in general, like big voids are increasing. Yes.
Wow. I see. Interesting. So, but these are predicted or explained by the general relativity, or you need a is it possible from general relativity you can predict this kind of structure?
Yeah, 100%.
Mhm.
That's what we do. You start from Einstein equations, but
Yes.
using Friedman Friedman equations now, which is just the diagonal of Einstein equation, right?
Okay.
For a metric. And basically, yes, you impose initial conditions, which is the amount of matter, for example, the velocities of the galaxies, Hubble constant, and so on. And that basically you use to derive equations for the galaxies. How would galaxies move in this universe, which is expanding and has this amount of matter? Right? The solutions of those equations basically will lead you to the formation of large-scale structure.
I see.
Right. And that basically is what you use to make these patterns that basically imply a filament or a void or a cluster.
Okay.
And then, well, what we're doing now is we do it with simulations. I think it's the path you would like to recreate because it gives you like a very realistic way to draw these motions of galaxies in the very big scales.
I see.
So now you have like cosmological simulations that reproduce that very accurate.
Wow.
Yes.
But you use general relativity, but there are research ongoing to modify or
Okay.
for example, like fit observational data more accurately
Right.
than general relativity predicts. If I understood the whole context correctly.
Yeah. Well, there's the issue that general relativity, which is very good model to predict things that happen, for example, in the solar system, it looks like it's incomplete at the very large scale, at cosmological scales.
This filament and void scale.
Yes, but not because of the filaments or voids. It's because of the expansion of the universe itself, right?
Okay, I see.
Yeah, here's where the cosmological constant enters, right? Basically, you need a cosmological constant to explain expanding universe using general relativity, right? So yeah, that's something that we fit to the observations, right? But yeah, it's not the only solution, right? That's something that Einstein did 100 years ago, and of course it was impressive, right? Nobody did it before, so everyone started using it.
Yes.
But of course, it's not the only solution, right? You can use this cosmological constant in different fashion to produce the same universe, right? Meaning that you can modify parts of the equations to get a similar answer. Okay.
Instead of adding a constant.
Yes, exactly. You can, like predict or use a more complex way to describe the universe that wouldn't involve a constant, right? That's what we call modified gravity.
I see.
Yes. And it's modifications you can do to, in general, you start from general relativity because it is what we can use more broadly, right? But by doing modifications to the theory, yeah, you can reach to similar observations. But yeah, it depends how you define a physical model. Basically, you need three parameters in your model that you would like to try to explain both physically and with observations, right? In that sense, general relativity, in my opinion, works very well because it uses only a few parameters plus this cosmological constant to explain this expanding universe. But yeah, it's not the only option.
I see.
You can modify parts of the equation to get similar answers.
I see.
Yes.
I see.
Yes.
Do you personally believe, or if you have to bet, like, do you think like cosmological constant is a way to describe or this modified gravity? I know it's
It's a
intense
Nobel
research.
Prize question.
Okay.
Right? If I have an answer, I will have a Nobel Prize, which it's not the case. But yeah, I mean, you have two options. Trust general relativity
Yeah.
and find an explanation to cosmological constant that is within general relativity, right? Which you can do. Like the one is favored in sense of logic is the vacuum energy. We think the vacuum itself can produce energy that could create this expanding universe.
Vacuum itself has energy. That's
Yes.
cosmological constant.
It's an option.
Okay.
But then astronomers try to measure that and they have a completely wrong number.
Oh, really?
Yeah, that's called, I don't remember the name, it's kind of like cosmological catastrophe or something. But basically, it's a difference of 120 orders of magnitude between the theoretical value of lambda and the one we observe.
Oh, that's 10 to the power of 120.
10 followed by 120 zeros.
Wow.
Between the number you measure and the one you predict from theory.
That's big difference.
So yes, and that's kind of the whole point. Like that basically tells you that it's very unlikely that vacuum energy is lambda. Okay.
Yeah.
So what other explanation you have? Not so many. Right? That's what we go and we have theories that modify gravity that try to consider this solution for lambda, like give a physical explanation, nature, right? And sometimes it comes directly from the equations. Like you modify slightly the equations of general relativity, you can get a universe that has expansion, right? And then you can fit the numbers with the observations, and that would predict kind of like different behavior for these filaments or voids, right? So you try to constrain or try to measure if these predictions appears in the observations. So that's what I'm trying to do in specifically, for example.
I see.
Yes, try to find if by these modifications of gravity, you can find the number that explains the same universe I observe and is predicted by general relativity. Yes.
Wow.
Yes. At this point, that's why it's an open question, right?
Yeah.
It becomes like very unlogical in sense of what you measure and what you expect, right?
Yeah, I don't want to believe if it's that big difference.
Yeah, no, it is. It's
see.
a very common problem we find in the science book. Like,
I see.
It's very well known. And so far, we don't have idea why.
Why?
Yes.
Wow. So with this modified gravity, in theory, should be able to predict or tell in what distribution or the matter would be a little better. No, better than.
Better in the sense of now the expansion of the
Okay.
universe will have physical motivation.
I see.
It will come from the equation.
I see.
It's not something we introduced by hand like Einstein did with lambda.
I see.
So that's basically favor in the sense of what's the physics behind this expanding universe, right? But yeah, it will explain observations better in that sense.
I see.
Like, I can now explain where is this dark energy that produced the expansion coming from.
I see. I see. So with this, I think I read through a little bit about the basically the cosmic voids is one of the important
it's a
places
nice
you
observable.
can test.
Yes, because they have little gravity, right?
Limited gravity. So
like there's not a lot of matter inside a void. So you know that if there's modifications to the gravity, it could be measuring a cosmic void, because what happens is that in different regions, like clusters of filaments, this new physics that comes from modified gravity is hidden. Like gravity is so strong that the modifications will be almost nil, almost zero. So they will be difficult to measure.
Like our galaxy too. They are
in our galaxy, that new physics will be hidden because general relativity is good.
It's
very
good.
Everything, right?
I see.
So yeah, you need to go to the scales where general relativity would fail in the sense of, okay, if there's modifications, general gravity is no more, you have modified gravity. So cosmic voids are a good candidate to show that if there's new physics, it could appear around there. Yes.
So that's kind of a universe experiment place where you can test
my
your
laboratory
theory.
is the whole universe. It's true. It's good and bad, because it's good because it's so big that the statistics is usually good. You have a lot of numbers to play with. But it's bad because you only have one, right? So you cannot repeat the experiment in different conditions. So for science, that's not ideal, because one of the key points of science is this can be replicated.
Yeah, replicability, yes.
Exactly.
I see.
You cannot do that with cosmology because you only have one universe. Yes. So it's good and bad, but I like it because it's so big that
that's
you do anything.
Yeah, come to think of it, that's quite not non-reassuring. You only have one universe you can measure.
It's true. It's one of the reasons why we use simulations a lot, because you can recreate different parts of the universe, like different volumes.
I see.
And you can also input like modified gravity, so you could predict how a modified gravity universe would look like. Yes.
Okay. Let's talk a little bit about another another role in our universe, the dark matter. We
Yeah.
haven't talked much.
Yes.
What are they? What is it?
True. Yeah.
Yeah.
Nice question. Well, it's dark, so we know it doesn't interact with light at all. Like, we can observe it basically.
Mm-hmm.
So again, it's
Yeah,
hard to
it's
know what it
visible.
is if you can observe it, right? That's,
Mm.
that's the whole point of science. But we can observe the impact of dark matter in our universe. What I mean by that is that things you observe sometimes don't match the things how they behave.
Yeah.
And that was the way dark matter was found. Like,
Yeah. How did they observe or first found
yeah,
that?
you will look at galaxy clusters,
Mhm.
these very big objects of hundreds of galaxies. And if you measure, for example, the velocities of these galaxies, that would be, by conservation of energy, that is, physical law that we know, you could calculate the mass of the object, like
Mm.
just by looking at velocities of things, how
Mm.
they're orbiting the object.
Yes.
So if you count the galaxies now in terms of mass, there's not enough mass to basically explain why galaxies move at that velocity.
The rotation is faster than
It's faster.
it should be
Exactly.
with only visible matters.
Exactly.
I see.
Yeah. So it's kind of like contradictory. Like, am I missing something? Is something that I can observe?
Mm-hmm.
Not in principle, because we have nice telescopes that can observe to a given magnitude. So even with all the matter you count from galaxies, even with the ones we don't observe because we missed them, there's not enough mass to explain those velocities, right?
Mm.
So what cosmologists, myself included, believe is that there's some matter that we cannot see, but it's there.
Yeah.
And it's making galaxies move faster
It must be.
by gravity. Must be, yes, because it's one solution, right? Again, you can also modify the theory.
I
right?
see.
But with the theory we have, there must be something we cannot see
I see. I see.
that is there. Yes. And that's how that matter was proposed. And it wasn't the old experiment. You can repeat the experiment within the galaxy, like in our Milky Way. And you can measure same, like velocities of things around the Milky Way, like satellite galaxies, right? You will also find a disagreement between the velocities you expect and the ones you measure, right? And the only way to explain this within the physics we know, or the model we accept as correct, is by having this structure of dark matter where a galaxy is embedded inside that would explain the velocities of the satellites of the Milky Way. Right? So it's not just you have to think of this like a sphere where the Milky Way on the center, roughly, right? And the things are moving around the sphere, right? So it's not just the Milky Way on the center, it's a whole distribution of matter, dark matter in this case, that is within this sphere.
I see.
And will explain the motion of these galaxies around.
I see.
Yes. And yes, when you do that, you say, okay, by explaining these velocities, the object inside the halo of the Milky Way will have this mass. And that basically is in agreement with the CMB, for example, because CMB would also predict the amount of matter, like the total matter we have to predict those patterns.
I see.
So those numbers are in agreement.
Wow. I
Yes.
see. So those dark matter distribution around the galaxy, are they like also uniquely distributed, or they will distribute it in a cluster,
Right.
or more dense in the center of the
Exactly.
galaxy, and then it will become
the
sparse and
motion of
sparse.
galaxies give you what we call a mass profile.
I see.
That will give you the shape, and that's something you can recreate in simulations, right? So by the simulations we know the universe is around 70% dark energy expansion, but it's 25% dark matter, or matter in total, where you have dark matter and baryons, everything we observe, right? Basically, a universe with amount of matter, yes, will give you a very well-known profile of dark matter that basically tells you this is how these particular spheres where galaxies live will look like. Yes, and those are the ones we use to again recreate these filaments, these clusters, and exploit.
I see. And one of the effects you observe with this dark matter is what we call like weak lensing.
Yes.
And that's, first of all, what's the difference between like strong lensing.
Yeah,
If
and
they,
with lensing.
if we call it weak, they should be strong, right?
Exactly.
So
Yes,
what are
yes.
the differences? And if, like for example, weak lensing is so weak or subtle, how do we
Right,
observe? How do we measure that?
Yes. Yes, as I was saying, the universe roughly 25% matter, right?
Mhm.
Meaning that gravity will react to that amount of matter,
Yeah.
right? So, and it's something that you observe, like even light will be curved by the presence of matter, like what happened with black holes, for example. Like light cannot
Yeah.
escape black holes, right?
Splendid. Yep.
Meaning that the light will react to matter in the universe, right? So there is this effect that's predicted by general relativity that basically will tell you that in presence of matter, the space will curve, right?
Mm.
Meaning that the light that's traveling through that space will also curve, right?
Yeah.
So you have this deflection of light caused by matter. That's what we call a gravitational lensing,
I
right?
see.
Big amount of matter in the middle.
Mm-hmm.
There's an object in the back that's very bright. There's give it light, and the light will curve just by the presence of the object in the middle.
Because the space and time
Is curved.
around the matter is curved.
Exactly.
I see.
And that's something you will observe from
see.
Earth, from your telescope. Right?
I see.
So yeah, if you take a picture, you will see these arc patterns that we call the lensing effect, right? Because it acts like a lens.
Mm-hmm.
It deforms light, basically, right? So what things can lens light?
Yeah.
Very big objects. How big? Like clusters of galaxies, for example. Not only clusters, but those are the ones we find these very nice arcs.
Yeah.
Those are the strong lenses.
Yeah, I remember I first watched that image from the JWST's
for example.
for images. I
Yes.
I didn't know that effect, and I was so
really?
amazed. Like
Yeah, it's quite impressive.
yeah,
Yes.
it's really round shape.
Yeah. At the beginning, you may think, "Oh, my camera's wrong.
Yeah, exactly.
My telescope have
something is wrong.
it's broken or something, right?" But no, it's something predicted by the theory, right? So you look at it and it's there. Like when you look at a cluster of galaxies, like it's very massive. We're talking about trillions of the mass of the sun.
Yeah.
10 to the 12, 10 to the 15,
Wow.
right? Things are behind that will appear distorted, right? Basically, what you get from the equation is a deflection angle, right? If thing is behind, because the way the object gives light, that will give you a deflection angle. So the light that's coming this path will be curved like this.
Yeah.
That's basically mathematically calculated by a deflection angle.
Oh, okay.
Right?
I see.
So that's something you can measure directly as a measurement of the mass of the object.
Yeah, so that's how you know how heavy it is.
Exactly.
Okay.
Yes. So that's how we know there's dark matter as well, right? And basically, yeah, that's what we call the strong lensing. Because you can measure it with the ruler. You take a picture, you measure the object is original here because sometimes you can observe it, right? The dark matter is invisible, so it's not blocking the object, right? And you see the distorted image, right? So you can measure the distance, the angle. That will give you the mass.
Yes.
Right? So everything you can do like that is a strong lens, strong lensing.
I see.
But yeah, then you can do the same exercise for slightly smaller objects like galaxies. Galaxies have a mass of 10 to the 13 solar masses, so 10 billion, something like that, right? That will also distort light, right? Okay. But it's harder to measure.
It's subtle because the bending is super subtle. Okay.
So what you need is you need two things. Many galaxies, like billions, maybe millions or billions. And you need to create like a mean deflection, right? So it's not now things behind the object, it's things around the object, right? That will basically distort the shape of a galaxy. So galaxies, you have them usually a spiral, which is a disk, or more spheroidal, right? So those can be distorted, like when you take a picture of them, right? You can assume that the main distortion of the shape comes from lensing as well. Okay, so that's something you can measure statistically, right?
I see.
In many galaxies.
Many galaxies.
In average, the distortion will be like this, right?
Yeah, because it's so subtle, you don't want to rely on only
you don't
one
do it
measurement.
one by one.
Yeah.
You need a bunch of galaxies, so that's why we use images in telescopes to measure in average what would be the distortion produced by a mass.
I see.
Yes, and you can use that to infer the amount of matter in the universe, which
Mm.
again agrees with the patterns from the CMB that would also give you that information. It's a very good observable to do cosmology, and that's what telescope like Subaru telescope do.
Yeah.
Yeah.
So yeah, you just mentioned the Subaru telescope that's
Yeah.
in
Hawaii.
Hawaii,
Yes.
and it's started operating like last year or 2 years ago, or recently? Not
2018,
okay, sorry.
but the data came roughly every 2 years.
Okay,
So the last release is this year, actually.
Mm,
So there was an important release 2 years ago. Yes,
mm.
exactly.
And it's already given quite important data.
Absolutely. Yes, it's one of the main. So the nice thing about HSC
Mhm.
is that it can measure a lot of galaxies because the telescope is big, right?
Mm.
If you compare it to other telescopes, it's bigger, right? Meaning they can go deep. So
Mm.
HSC is good because of that, right?
I see.
Even though the area that the telescope surveys, like the footprint, is slightly smaller than what you get from other telescopes, just because the amount of galaxies you get from HSC, you get like good statistics. And it's basically what we use to forecast what future telescopes like LSST will give you, right? So it's very important experiment.
Mm.
And it gives you, again, very accurate measurements of these numbers.
I see.
Yes.
Okay. So yeah, so those telescopes are very like our technologies are very important
Mm-hmm.
to make accurate, precise measurements.
Yeah, of course.
So that we can unveil the curtain of the universe.
Yeah, that's a neat part of astronomy. Like
Mm.
it goes with technology,
Yeah.
like astronomy and physics in general. Like use the technology, but also moves it forward. So sometimes we need bigger telescopes, right? So sometimes you need a new technology that's capable of moving those telescopes, right? So basically, we provide technology to all the sciences, humanity at the end of the day. Yes.
Yeah. Okay. Let's go to a topic of black holes.
Oh, I like black holes. Yes. Yes.
So let's start with let's actually start with what excites
Yeah.
you about a black hole.
What excites me about a black hole?
Yeah.
So they're very interesting objects in the sense that they can be described with a few properties, but at the same time, they drive a lot of physics. They appear in many, many areas of physics, not just astronomy. They're in quantum physics, they're in cosmology, in stellar astronomy, and so on.
So they're everywhere in the physics realm.
Yes, in terms of the theoretical physics, for example, or the physics that are trying to explain the origin of things, they appear in many branches of physics. So they become really interesting objects for physicists like me, right? And I'm pretty sure many other physicists share the same opinion. Right?
Mhm.
So yeah, that's what I like them. Like they are these, in theory, simple objects, but at the same time, that's so complicated.
I see.
Yeah, they're compelling.
Oh,
Sure.
wow. Okay. So you said it's simple object. So it's explained by only by a mass, spin, and possibly charge. And is
Mass,
there any
charge, spin, which is like angular momentum.
Yep.
I think that's all. They have temperature, but I think that came after like you do some very complicated physics that I'm not expert on. But yes, it's just 4 or 5 properties. Yes.
And that's what they call like no hair theorem.
Yeah, I always like the name because no hair. What's that mean? Like it's bald, which is I think the kind of the point. Like that's soft. There are soft layer where you have the horizon of the event horizon of the black hole, right?
Yeah.
So nothing happens in the surface per se. Like
Mm.
it only has if it's moving, yeah, of course, it's rotating, right?
Yeah.
But there's no dynamic associated to that. It's just a property of the black hole. Same with the charge, same with the mass. Like, of course, inside the black hole, there might be a singularity, which is basically where everything ends up, right? But the event horizon is like this membrane and a layer that basically limits the physics that we use actually. And that's what they call it, like no hair, because nothing else happens there, right?
I see.
Yeah.
I see.
Yeah.
So but the information
Uh-huh.
of the stars,
Yeah.
that like what made up these stars, or what's the composition, or
What's a black hole made of? That's the question.
no. So black holes. Then first, probably I should ask like how these
is it
black
made?
holes are made.
Yeah, good question. We think we come from stars.
Mhm.
Because they're in the sky, right? So it would make sense. They
Yeah.
come from things we can observe, right?
Yeah.
So that's a stellar black hole, basically,
Mhm.
which is few times the mass of the sun. So that's you have a star that's heavy, heavier than the sun,
Mhm.
and by the end of its life, when it becomes supernovae, if the star is massive enough,
Mhm.
the pressure is not enough to win to the gravity,
Mhm.
meaning that the thing will collapse in itself. So it's kind of like an implosion.
Yeah.
Right?
I learned that there is like a theoretical, no, actually like a theoretical limit of the mass.
Yes,
You
actually,
can
you can
precisely
calculate. Yes, because the star burns fuel, like it's hydrogen, basically,
Mhm.
to generate heavier and heavier elements. We can calculate the pressure, which is things that goes against gravity, right? So the star is formed by the fight between pressure that points out and
Yep.
gravity that points in, right?
Yeah.
Yes, everything that has a higher pressure will lead you to a star, right?
Mm.
When the star burns all the fuel, it will become a supernovae, but in the center you will have a white dwarf, right? Which the pressure of the white dwarf is not anymore the one caused by the fuel. It's caused by quantum physics, like electron pressure, for example, or neutron pressure for a neutron star, right?
Okay.
So it's more quantum, right? So that's the limit is roughly above 1 solar mass. 1.4 is the Chandrasekhar limit. Beyond that, there is no pressure that can win to gravity.
Because so massive.
Yes. So the core of the star will collapse.
Mm-hmm.
That will lead you to a black hole. Like again, general relativity predicts that.
Yeah.
Right. So basically, that's the origin of the black hole. Right. After that is this object with a size given by the Schwarzschild radius, which depends only on the mass, right? But that will give you an object that we can call a black hole. It's not the only option, because we have supermassive black holes that we believe are the seeds for galaxies. So for a supermassive black hole to form, this probably happened in the early universe when the universe was young. But the same effect, there were massive objects, probably early stars that formed when the universe was young. But then when the universe grew in the inflation period, just after the Big Bang, the universe become very big as we have it now, roughly. That basically made all the objects there to grow as well. Right? So now these early stars became objects of 10 to the 13 solar masses, right? And that would, or 10 to the 10, roughly, yeah. And that would be consistent with things we find in the center of galaxies, including
like
our
ours.
galaxy.
I see.
And yeah, that's what they did. They took a picture to the center of a galaxy. This is the Event Horizon Telescope. They basically recreate what would it be in the center of a galaxy. That's something that you can also measure with the motions of the stars there.
Yeah.
And that basically is the picture of the black hole
Yeah,
that came
that
5 years
phenomenal
ago. Exactly. It's a
images
very
that,
nice image.
yeah.
Yes. And those are supermassive black holes. So we're talking about 10 to the 10 solar masses at least. So they have different origins, right? But they all respond to the same physics,
I
like
see.
the black hole physics.
I see.
Yes.
So they're like simple and they're made from the stars, or the collapse of the star, or in the early era of the universe they made up the same origin, in the sense that it's coming like collapsing.
Exactly. A massive object that collapse.
Yeah. So but you said that the black holes we can describe with only a few parameters.
Yep.
But in these few parameters, do we also expect the information of like the star composition of a star is preserved in like in terms of information preservation
inside the black hole?
Yeah.
It's what they call the information theory. So what you call information It's basically everything. Like information is, in this sense, is kind of like a quantum definition, right? Means that the state of any particle you can calculate in units of information.
Okay.
Right? Bits, for example.
Bits.
Bits is the unit of information, right? So everything has information in that sense because, but yeah, you have to go to the quantum state of particles to measure that information, right? But yeah, everything that enters the black hole enters as information because it means all significance as an object, right? Like it gets disrupted by gravity.
Yeah.
So you don't have a star inside a black hole. You have the information that makes the star, basically. So yeah, you can measure the amount of information that enters a black hole. And that's something that quantum physicists or particle physicists do, right?
Okay, so the information itself will be like preserved in black hole.
Yeah, information is probably just another way to describe like energy conservation.
I see.
So you can say information is also conserved. Yeah.
I see.
Yeah. But yeah, that basically leads, and that's something scientists like Stephen Hawking did, was to measure the entropy of the black hole. Because again, you have concepts of information with response to energy. And if you have energy, you can say you also have entropy. Right? Thermodynamically, that would imply that black holes have temperature.
Okay.
So it's something that scientists thought you wouldn't measure ever. Because it wouldn't make sense.
Yeah.
But Hawking shows that basically you can estimate the temperature of the black hole. But that would imply that the black hole at the same time has to radiate.
Emit something, yeah.
Yeah, because that's how you measure temperature.
But black holes should not.
They're black, right?
Yeah.
So yeah, no. Then you go to concepts of Hawking radiation, which is an explanation he gave to say you can measure this as temperature. And Hawking radiation comes from quantum physics once you explain what is called a virtual process. It's a virtual process.
Okay.
Yeah. It's virtual in the sense that, I mean, it's real because something is happening, but they call it virtual because it happens really fast. It's the creation of a pair of particle antiparticle that creates and annihilates almost instantly, right? So Hawking thought, and basically is what implies, is that particles that are created near the event horizon will lead to one of the particles theoretically escaping. Okay. So the pair of particle and antiparticle will be broken. Then one of the particles will go inside the black hole. Theoretically, the other one will go out.
I see.
So that's something you could measure in sense of a temperature.
I see. So they one is go inside, one is go outside, but they don't annihilate because one is already in the.
So the virtual process
hole.
is broken.
I see.
So that creates a radiation, basically. And that's the radiation of black holes.
Oh, it's not originated from black hole, but it's the like a particle, like antiparticle, the particle that
exactly. So that would basically imply that the black hole will lose energy because it's radiating.
Yes.
A very slow rate, very low temperature. We're talking, I don't know, 10 to the minus 100 of kelvins, like it's nothing.
Wow.
It's purely quantum, right?
Yeah.
But that will lead to black holes evaporating in a very, very long time. Yes.
Okay, that's black hole Hawking radiation.
Yeah, exactly.
And eventually they will also.
Yeah, it's the only way we think black holes can radiate energy. Maybe it's another way, we don't know. Hawking came with this explanation that at the time nobody would believe, but I think people will believe it nowadays, actually, because they do research on this, of course. And
I see.
Yeah, it's not has been measured because it's hard to measure, right? Super hard to measure, but in theory it could maybe. But again, in such a long time that for us it's probably not relevant. Yes.
Exactly.
Yes.
So there is the black hole you said is like enclosed with the event horizon, but if once you go inside, there's no way back, and it will eventually go to the what we call singularity. And so please tell me what a singularity is and what will we expect if you reach to the singularity?
Yeah, I don't have that answer.
Okay, yeah, of course. If you
Something
know
that
that.
we cannot know because we don't have the physics to explain it.
Mhm.
But yeah, once you derive the equations for black holes, like Schwarzschild equations for the size of a black hole, yeah, there are two limits. One is the event horizon, which is a Schwarzschild radius.
Mhm.
But there's also another solution that basically r equals 0 is where the singularity is. Okay, so it's a purely mathematical definition in that sense. Right?
I see.
But it would be at the center of the black hole. Right.
Mm.
To understand that, basically, you need to do a special relativity curves. We have what we call the space-time diagram,
Mhm.
right? Which is space is in the x-axis and time is in the y-axis. So time only goes up in this diagram, right? So light is light has a finite speed in every system of reference. So that's the special relativity part. So once you draw what is called a light cone, basically how an object moves in the space-time, the solution of that object, which moves in this light cone, always ends up in a singularity because the time moves in only one direction, right? So the singularity is like in the top of the diagram. I just draw like this seesaw pattern because it's kind of like disrupts everything. Like there's nothing beyond the singularity, right?
Okay.
So as you're moving in the space-time, in the space-time diagram, you only move up, right? You will end up in the singularity, meaning you will get destroyed, basically.
Okay.
Right?
It's the end point of the time or something like
Yes,
that.
exactly. So it doesn't tell you how it happened or what will happen.
Yeah.
Only tell you that you will end up there, and after that, you won't be there anymore.
Okay.
Yes.
So currently there's no theory that describes what will happen and
There must be. In my limited knowledge of black hole physics, of what happens inside, I think you can do some solutions. This is the Einstein-Penrose bridge, which is basically what they mean a wormhole.
Okay.
So there is a solution that basically tells close to the singularity inside the black hole. You can, you have to draw the diagram, but the black hole, in theory, will be connected to a white hole. That's the opposite of a black hole, right?
Okay.
Something that only emits; it doesn't absorb anything, right?
Yeah, it can easy
So
to-
in the solution of the Einstein-Penrose bridge, you can move to the white hole and appear in a different part of the universe. That's where the the wormhole theory comes, and
I see.
movies like Interstellar
I see.
kind
I
of like
see. But
approach to
it's
this.
not completely fiction, but it's like made from the equation.
It comes from equations,
I
like
see.
from a
Wow.
situation that you can mentally think, right? Then you can solve that, and yeah, you can appear somewhere else in the universe, right? And there's where science fiction center, which I also like, right? And yeah, you can play with that in that sense. Like,
So if that were true, the number of black holes in our universe and the number of white holes in the other universe should match.
yeah, I think so. It's not something I've done myself, so I don't have the answer. But yeah, that makes sense to me.
Yeah, that makes sense.
Yeah, but I think that also predicts like multiverses even, so it becomes really complicated in that sense. But yeah, probably there's a universe with only white holes in that sense.
I see. Interesting. So the one of the interesting thing about black holes is the gravitational waves.
Oh yeah, yeah.
Not only black holes, the neutron star when they're
When they merge. Yes.
the LIGO detected gravitational waves, and but how do we like what it can tell, like gravitational tails, what they can tell us about this universe?
Yes, very good question. So we have explanations for black holes, but yeah, I think we're also interested of from the beginning of the universe until now, how many black holes are there, for example?
Okay.
Yes, like I do a mass black hole, a mass function of black holes. Yeah, meaning as function of mass, how many black holes do you have?
Okay.
That could solve some problems like the nature of dark matter, for example. One candidate of dark matter is primordial black holes, for example, black holes that create in the very early universe.
Mhm.
So yeah, because we don't see them now, we cannot see black holes directly, right? They could be part of dark matter. Probably not all the dark matter, but a big part of dark matter, right? So that's something we would like to calculate, right? So if that's the case, if there are many, many black holes, some of these black holes will be like in this binary state, like stars, right? So those are the ones that would generate gravitational waves, right? Not only, but in a higher fraction, right? Yeah, we would like to measure those. So you need to measure the gravitational waves,
I
right?
see.
How do you do that? Again, quite difficult, but LIGO basically does interferometry technique, which basically literally measures the effect of these gravitational wave ripples, like the wave moving through us.
Mhm.
Basically, it curves the space time as well. Yeah. So that's something you would like to measure with an interferometer. So LIGO, what it does, and not the only one, because most of the interferometer for gravitational waves are like this.
Mhm.
They have this kind of L shape. So one moves this direction,
Yep.
the other one moves this direction.
Mhm.
Okay? So the way gravitational waves moves will impact on the way the interferometer moves. Once you isolate all the possible signals that would move the interferometer, including earthquakes, for
Yeah.
example, once you get rid of all that, all the signals that are like noise, you would be measuring the gravitational wave if the interferometer is moving.
Yeah.
That's what LIGO did.
Mhm.
Right? And why we know that was the case, because for the first observation that was successful from LIGO, they also measure the electromagnetic content part of this object, meaning the one we can observe with light
Okay.
in the optical. Right? So they noticed this neutron star merging, which was consistent with the signal they found from LIGO. Right? So again, the theory predicts how would the gravitational wave be measured by the interferometer, by LIGO, right? And at the same time, because something they did with collaborations with other telescopes, they say that in this region, there was a neutron star merger that is consistent with the signal that LIGO measured. Yes.
Wow.
So that's what the first detection that
Yeah.
happened in 2017. I
Mm.
was still a student by then.
Mm.
But yeah, it was quite revolutionary.
Yeah.
Right? It was something that some people would know that couldn't be measured, right? But again, it's a bit of luck because they found this optical object consistent, right?
Mhm.
But at the same time, it's because it comes from the theory, right? It's something that we like to predict, which is again another success of general relativity. And since then, we haven't stopped. We have in the order of probably few tens or maybe even 100 of events that we call them events because they are like something like a measure. Some of them have this electromagnetic counterpart that we can observe.
And check if it's correct.
Exactly.
Yeah.
And some of them are black holes, like black hole binaries. And we use them to measure their mass because, again, the more important quantity in this case is the mass of the progenitors. That is what is used to measure this. LIGO will give you like many of these objects. And future experiments, of course. There's one that uses interferometer, but from space telescopes as well.
Yeah.
So you can do a different kind of technique, but those can measure also bigger gravitational waves.
Yeah.
Yeah.
I think I've heard of that LISA project.
LISA Einstein telescope.
project that
Yes.
put the spacecraft in a fixed position, in a fixed length, so that you can basically have a longer distance between interferometers.
Yes.
If you're in the ground, I think LIGO was something like a few kilometers in the
Exactly.
arm wide, but in
Yes.
space, you can place 100 kilometers or something like
That's
that.
exactly the future of this part of science, like combining several ground-based interferometers, like LIGO. There's one in Japan for sure, in Europe, in South Africa, plus the telescopes in the sky, in space, that would also provide new measurements.
Yes, that would be really super cool.
Yes, then you can do more science with galaxies as well, right? And that basically would complete this missing part of the. Well, you have observations in the whole electromagnetic spectrum, right? From wavelengths of radio frequency to gamma rays, right?
Yeah.
But we were missing this gravitational wave counterpart, and that's
Yeah.
something that these experiments will complete.
Yes.
Mhm.
Yeah, I did one podcast episode with another person who was studied
Oh, great.
theoretical physics in
Yeah.
the university. And when we were talking about it, we thought we talked something like that gravitational waves
Yeah.
will give you another spectrum of the world, because
Exactly.
we've only seen in electromagnetic spectrum.
Yes.
But gravitational waves is completely different. And come to think of that, for example, can you see through the early stage of universe with gravitational waves? Because we only know that the visible lights, electromagnetic waves,
Yep.
we can only measure about 300,000 years after the Big Bang.
Yep.
But if we have gravitational wave, can we see through it and then see even farther?
Yeah, it's a very good question.
Yeah.
I think that's kind of like we are betting into. Like, yeah, optically we have the limit of photons not being visible behind the
Right.
CMB, right?
Right.
But that's not right. That's not the same for gravitational waves.
Yeah.
So we can measure gravitational waves from all sources.
Mhm.
Yes, you are quite correct. Like, ideally, you could measure what will happen between CMB 3,100 years ago. Since Big Bang and the Big Bang, right? So that's the part we're missing right now. And it's important because you could solve inflation, which is this very enigmatic time just after the Big Bang, where the universe grew in this completely crazy rate. So it became inflated. That's what we call inflation. That would definitely produce what we call primordial gravitational waves. That, if you have an idea of all the sources of gravitational waves in the universe, that will also be added to the equation. So you can have an expectation of how would they look like, right? And yeah, if we measure those, we can prove inflation right, which is something we haven't done yet.
Yeah.
Yes.
Finally.
That would definitely complete our physical model a lot. Yes. But it's very challenging because gravitational wave background, basically all the sources, are definitely the more important components, either the black holes or things we have in the universe, right? But I think this primordial part is equally important, right? But also challenging to measure.
Do you think we will be able to unravel that in our lifetime?
Yeah, it's a good question. I think we could, yes, if they are correct, right? There's a chance they're not there, right? But yeah, it's part of physics that we can also do with CMB physics. Like, you need the polarized spectrum of the CMB, meaning that light is polarized. It has two planes.
Yeah.
One of them would be more affected by this physics. Right?
Oh.
So it's also an observable that we could measure probably in the next 10, 20 years.
Wow.
Yes.
Polarization matters
a lot. For CMB, it's one of the key components. For sure.
Wow.
Yes, it gives a lot of information. Not only about black holes or inflation, but the whole cosmology, amount of matter, Hubble rate, and so on. Yeah.
Is it because of the polarization give you some feature, if that is does it explain something about the states of the source of the light or something like that?
Yes,
I see.
like that. Yes, the light we get from CMB,
Mm-hmm.
one of the components, in this case the B component, will be more will be affected by the physics of the early universe.
I see.
Yeah.
I see. And it might be polarized in a vertical, horizontal, or spiral way.
Yeah, exactly. It's a spiral way.
I see.
There's an angle that is quite well known that gives you information of this early universe physics. Yes.
we have light and gravitational waves, and
I know, right? That's very exciting. It's the nice part of this part of physics. Like, has a lot of things to think about.
yes, exactly.
Mm.
Another question I would want to have is, you can we use gravitational waves also to measure the distance? Because if we know that the absolute energy that the, for example, colliding black holes emit, and then we calculate how we observe the gravitational wave and an apparent magnitude of the gravitational
you will need
wave.
something like a apparent magnitude, right?
Right.
I think you could, but I think what is easier is to identify this electromagnetic counterpart, the one you can observe, for the same reason,
I see.
to locate them further, right?
I see.
But it will definitely give you information about the things that are harder to observe, maybe. Because black holes you can observe it, right? So you can observe only the neutron star ones, right? But for black holes in galaxies, maybe you can combine this with another of the techniques we discussed, like supernovae, and have a measurement of distance with that. So that would definitely complement our current observations.
I see.
It's what we're trying to do, like combine different experiments. So we have either information of gravitational waves, if we cannot see the sources, or reverse in case of having a location for the gravitational waves.
I see.
Yes.
Okay. Let's talk a little bit about data-driven discovery. That you also have been working on some using like simulations and also maybe using machine learning sometimes to discover insight or get insights from the data. So recently, I think we have more and more data, and do you think it will, like, having a lot of data will give you advantage, or having a machine learning technique will make you discover something new about the physics and
thanks for asking that. So the way we used to do physics is like you have a theory that you want to test, right? And then you do experiment. In this case, you grab your telescope and observe something, right? That was the classic way of doing physics, like for astronomy and cosmology. And that happens for hundreds of years, and we have nice theories and everything. But we're kind of like in the stage where the opposite is happening. We have so many observations, and of course, we have so many theories to try, right? But now it looks like the data is driven the science. That's what the name comes from, data-driven discoveries in this case. But it becomes important to have a way to process all this data that we observe from these big telescopes or from simulations, right? And have a way to try this data with all these theories we try to test, right? So you like to come with a efficient pipeline that basically takes the data, process it, test it with theory, right? And machine learning became quite useful for that. Like, you cannot just run all these simulations you want because they take time, right? You either like to use some of these simulations, train it in your machine learning models, and use the machine learning models to do physics at the end of the day, right? I would like to say it's replacing physics, but it's helping a lot on the way we do physics these days, right? Because it's efficient. It's an efficient way to do physics, right? You just need to train the network in some way. For that, you need a lot of data that we have, right? And then use the network to make some predictions, for example.
Especially when we have massive amount of data.
We're talking about petabytes of data per a few days, right?
The humans cannot see through all of them.
You will need a lot of PhD students. There's money, right?
I see.
Or a lot of postdocs like me. Right? There's not enough professors to do this, right?
Okay.
So,
okay.
You of course need a lot of handwork that we have. We have a lot of students everywhere and a lot of scientists. But the data is still too big. So you need something efficient. Machine learner responds very well to that.
I see. So have you ever discovered or get new insight from using machine learning?
So it helps a lot in things I do, like running simulations, for example, or dealing with the observed data, right? So yeah, I would think so. Yeah, like I mean, I cannot put the machine learning on the author and the author sections of the paper, right? Because you cannot hold the network accountable for things that are wrong, maybe, right? So I'm responsible for that, right?
Okay,
So
yeah.
I use the network for some things that, yes, are useful, quite useful. In sense of discoveries, not me particularly, but yeah, many experiments where this was done thanks to the machine learning part. I cannot do like all the work I do is based on simulations. Like my theories are based on simulations. But yeah, as I was saying, I cannot run simulations for all the theories I want to try, right? So machine learning, for example, I use it to kind of like interpolate what will happen between simulations I know and the ones I don't know, right?
I see.
So yeah, basically I use a network that would predict what will happen for all the possible alternatives of the theories I wanted to try, right? And use the best one to find the one that fits the data better, right? And this is basically the paper I did with the HSC data, right? We use HSC observations to create weak lensing maps of the universe, right? And infer the amount of matter, infer the amount of dark energy, and so on, right? And yeah, the machine learning part helped me to use all these observations and my simulations to predict the best results. And those numbers right now are quite competitive in terms of the current results or what we think are the correct ones.
I see.
Because sometimes you have like disagreements between different experiments, which is completely normal. It's a scientific process, right? It's not like you are wrong or right. It's that your data is telling you this, right? Sometimes those numbers don't match. Okay, that's right. But yeah, then you would like to come with an explanation, either physics you're not considering, right? That's where the modified gravity enters, for example, or things in your process, in your scientific process that are probably not quite correct, right? Machine learning helps you with that a lot,
I see.
actually. Yes. So at the end of the day, you would like to conciliate these numbers. And it's something that, in this case, my study did, which more or less studies that complement to each other, right? So you converge to this kind of right number that you're looking, which is related to the clumpiness of the universe, like the large scale structure, how it's distributed, right? So it's one of the numbers of the cosmological model that we try to understand, right? There's one measure with these observations.
I see.
And now we have kind of like a agreement of what's going on.
I see. Wow.
Yes.
Do you think in the future there might be a situation, for example, where we have lots of simulation data, but we only have few observational actual data, and if we compare these two, like usually we want to prioritize observational data.
Yep.
But if we have really big number of simulation data and then few number of observational data, which might be sometimes incorrect because of the measurement error or something, other effect.
Yeah.
Do you think it will be a situation where you start to like trust more simulation data over observation?
Yeah, I see what you mean. I think it comes of the sense that what's the data telling you, right?
Yeah.
Yeah, you would say, okay, it looks more like this simulation. It looks nothing like that simulation. And yeah, that's kind of what we do, right? So I think the machine learning helps you there, like to understand what it's like, for example, an anomaly, like what doesn't look like anything like the models we are, like the simulations, right? Machine learning is very well used for that, actually. Like what does look completely opposite of what you think is right?
Yeah.
Sometimes, that basically leads you to systematic errors in your observations, right? Or new physics, even, right? Like, I think that's what particle physicists do. Like, try to do experiment. They look for these bumps that usually means a new particle. That's how the Higgs boson was found, for example.
Oh, really?
And so on. Yes. With astronomy, it would be similar. I think in the future, at some point. once we find something that we think it doesn't belong there, it would be something new in astronomy or cosmology, right? I think it will happen a lot. Yes, James Webb found this kind of like early galaxies that don't belong there. Like they are formed too early and they're too massive. So,
Really?
yes. So they look like something in the theory is wrong. That could be a scenario, right?
Oh.
Some people say it's just the way they measure the redshifts, for example, is wrong. That could also be. But yeah, it kind of leads you to these new discoveries, which is something that happens every time. And that's also a nice part of science. Like nothing is completely discovered. Like every time, every day, you have new discoveries.
I see.
Yes.
Okay.
Yeah, and I think that's kind of like where we're heading. Like there are going to be these disagreements of the current theories we have, which will motivate new theories that we can try. Yes.
Okay, so that's how we should not be comfortable only with our current.
Of course, this is not a religion, right?
So
you have to question everything.
yeah,
right?
and you keep expanding your observational data, and you also expand or make more better world model ourselves.
Yeah. Personally, for example, I really favor general relativity, but it's not a perfect model, right? It's not like it has flaws, but it's probably incomplete, right? Of course, I'm pretty sure Einstein didn't want to, have a complete theory, right? He knew it wouldn't be complete, right? So it's up to us to, corroborate if the theory is right or find new things, right? And that's kind of like what we do. Yeah.
Yeah. Well, Joaquin, thank you very much today. It's really interesting.
Thank you. Your questions were very good. I really like them. Thank you.
Thank you.
Mm-hmm.